question 6M2 from Statistical Rethinking, second edition. So before you run any of this code, make sure you have installed and loaded the Rethinking package with these first two code blocks here. And let's get into it. Okay, so in this question we are talking about multicollinearity, which, if you recall from earlier in the chapter, is when two predictor variables that the estimates of two predictor variables, or the beta coefficients for two or more predictor variables, is highly uncertain, and these predictor variables are highly correlated. Okay, so let me just read the question here. So sometimes, in order to avoid multicollinearity, people inspect pairwise correlations among predictors before including them in the model. This is a bad procedure because what matters is the conditional association, right, rather than just mere association or correlation, is the conditional association among the variables in the model. To highlight this, consider a DAG, which is just a mediator or a pipe, X, Z, Y. Simulate data from the DAG so that the correlation between X and Z is very large, then include both in a model prediction, so predict Y with X and Z. Do you observe any problems with multicollinearity? Why or why not? What is different from the legs example in the chapter? And if you remember the legs example in the chapter, there was height. We were predicting height based on left leg length and right leg length. Okay. So let's go through here. And so first we're going to simulate 1,000 observations according to this DAG, okay, into our pipe. And I'm going to use the variable m instead of z because it helps me keep these things straight in my head. But I'm simulating data, so I have x, and it's not attached to anything, or it's its own values, randomly created values. And now I have m, where the mean value of m is x, okay, plus and a standard deviation. And then I have y, and again the mean value of y is m, okay. And so hopefully you see how that reflects the x to m and m to y pipe. All right, and I'm just going to package all of this. Let me run that. I'm going to package all of this into a data frame. Okay, and then I'm going to get the correlation matrix for the data frame. That's why I put it in the data frame in the first place. Okay, so I have the correlation between x and x, which is always 1, of course, x and m, which is very high, and x and y, which is reasonably high. Okay, and then I also have the correlation between m and x, which is the same as x and m and m, and m and y. Okay. All right. So now we're going to, the important part here, according to to align with the question, is we have a very high correlation between x and m. And so we need to figure out, is this going to cause a problem of multicollinearity? And we should see this problem of multicollinearity if there is very uncertain estimates of the beta coefficients for x and m as we predict y. Okay, and I'm going to run a kind of exaggerated model here because I want to come back and use some of the information from this bottom part. Okay, but I have my model, and so here I am just modeling the value of y with x and m as the regressors, but I'm also going to have a linear model in here for the relationship between x and m. Okay, so this is the relationship for y with x and m, and this is just for m and x. Okay, so I run this, and I get my output. Okay, and so so the model relevant to us right now is just this top part. Okay, and we want to look for we want to see if there's signs of very unstable estimates for beta xy and my. Okay, and there doesn't seem to be, right? So if you go to the standard deviations, these aren't huge standard deviations, And if you look at the credibility intervals, they are both, even though this one does kind of trespass over 0, they are largely on one side of 0 at least. Okay, and that's not what you would expect in multicollinearity. Again, hopefully you've read the chapter and you understand what these would look like. If there was multicollinearity, we would expect the credibility interval, for instance, to be pretty evenly distributed and widely distributed across 0. Okay. So now the question is, okay, so do we see any multicollinearity? And I'm arguing no, but why? Okay. Now the reason why took me a while to formulate. But what it comes down to this. So in order for multicollinearity to take place, hold on, I have to cough. Okay, so in order for multicollinearity to take place, the explanatory variables, in this case x and m, need to be sharing duplicated information with y, and not only duplicated information, but direct information, right? So in the DAG, direct information would be represented by that arrow. Okay, if I'm going through more than one arrow, it's indirect information. All right, and so multicollinearity stems from direct information being duplicated among explanatory variables to the outcome variable. All right, but that's not what's happening with a pipe. Okay, why? Well, because X is not sharing any direct information with Y. All of its information is being filtered through M. So the only variable that is sharing information with Y in the case of a pipe is with M. Okay? So there is no duplicated information, or not much duplicated information, between X and M. All right? So contrast that with the example earlier in the chapter in which we were modeling height with left leg length and right leg length. Okay? And the way that data was formulated would conform to a DAG like this, where height was the cause of both left leg and right leg. So notice here that the cause, which normally we would try to put in as an explanatory variable, the cause is actually the outcome to the regression. And the effects, left leg and right leg, are the explanatory variables in the regression. Okay? And so now that means that that means that height is the cause of both of these things. And so that means that there's information being directly shared between left leg and height, and there's direct information being shared between right leg and height. And in fact, this information is duplicated. Okay? It's the same information being shared of height between these two variables, right? Height is changing, and it is sharing its information with left leg, and it's sharing the same information with right leg. Okay, so we have duplicated information between these two predictor variables. I don't want to call them explanatory because they're really just predicting. They're not the cause of height. Okay, and so because there's duplicated information in that example, we have high collinearity. Okay. Well, okay, so that's my answer to that. And then before I close out here, I think that there's something more, a more general point to make here, okay? And that is that our correlation coefficients, okay, and our beta coefficients are they both represent some kind of relationship between variables, okay? And so we might expect that correlation, say between X and Y, is somehow proportional, maybe not equal, but maybe somehow proportional to the beta coefficient for X on Y, okay, and similarly for M. And so let's just empirically look at that. So if I guess I've already ran that. Okay, so here I have the different relationships, X and Y, M and Y, X and M. And I have the correlation coefficients that were found as well as the the regression coefficients and correlation coefficients that are found. Okay, and you'll notice that these don't seem to be proportional as we go across, right? This is a very large difference, and then those differences kind of they vary. In other words, okay, and so all of this is to say that correlations, of course, are not beta coefficients. Okay, and why not? Well, it's because beta coefficients are considering every other variable that may be impinging on the outcome. Okay, whereas a correlation is not considering those other variables. So, for instance, this beta coefficient between x and y is considering the relationship between m and y. Okay, but the correlation between x and y does not consider the relationship between x and m and y. Okay, that's it.